I bought a copy of Sabine's book, and it's really, really depressing me, but I thought I'd say why. Her career has been in, I think it seems like it's been high energy physics mainly, and that gives her this high energy physics view of physics. And what high energy physics is about is the so-called structure that's revealed in atomic and subatomic structure at high energies. And high means the kind of mega, giga and tera electron volt energies that you find in colliders, particle collider experiments like CERN's LHC. And by analyzing the collisions of particles in these accelerator rings, you spin the particle round and round so that you have this ring which is made of a huge number of superconducting magnets which confine a beam, a particle beam. I guess they all have to be charged, and these particles fly around the beam, and there's a similar thing actually that happens inside a microwave oven, but at a much lower energy. The magnets act as a kind of guide, wave guide, and the particles are confined to this space, so they become a beam, and then at various points on the beam line you can take off a part of the beam. Presumably they select it by the amount of energy that they want, and the kinds of particles that they're looking for, I'm not sure. But it's like little, they're not pit stops because the particles don't ever re-enter the ring, but they're points where the beam can be analyzed. And I guess they can shoot the particles into blocks of metal or crystals or I don't know what, and inside these crystals the products of the particle collisions, the things collide and split atoms and do all sorts of things in the experiment. So they take the beam off and they whack it into something, and then they look at the debris and they measure the speed at which the particles move out of the collision zone. And they also have another set of electromagnetic fields which allow them to trace the debris as it passes through the detector. And these detectors are kind of three-dimensional structures, but at each point in this three-dimensional grid around that makes up the detector, there are little sensors which can detect the presence of a particle at a certain time. So then they have a computer which watches all of these points, and the computer collects all the data about which particle detectors were triggered at which moments, and then all that data is then analyzed statistically in order to infer what sort of particles these were, depending on the way they behaved in the electric field. If they pass straight through, if they travel in straight lines and they're not affected by the magnetic field, then they're presumably not charged particles. So it's that kind of level of thing. So these inferences are being made on the basis of the tracks of the particles through the detector. And it's very expensive and hard to do these experiments. But the point is that gives you roughly an idea of what particle physics is about. And the models, the mathematical models of physics predict what will happen. And here she talks about, where shall I start reading? She's talking about the separation of scales and decoupling. So I think I have to start here. Nature, it seems, caters extremely kindly to our desire to understand. Whatever happens in the nucleus stays in the nucleus. We only see the net effect. Some atoms bind with hydrogen, others don't. But what exactly goes on in the nucleus has nothing to do with this bond. Some atoms form regular periodic lattices, others don't, and what happens in the nucleus has no influence on the lattice structure. It's not only for atoms that we can ignore exactly what the constituents do. Properties of composite particles, such as neutrons and protons, are also almost unaffected by the motion of their constituents, the quarks and gluons. And when we describe, for example, the way that atoms push around grains of pollen on the surface of water, I didn't realize it was on the surface. I thought it was actually in water. It's Brownian motion. It is sufficient to think of the atoms as particles in their own right and just to ignore that they're made of smaller things. At even larger scales, it's the same thing. The orbits of planets don't depend on planetary structure, and zooming out some more, on cosmological scales, even galaxies can be dealt with as if they were particles without constituents. This isn't to say that what happens at short distances doesn't have any effect at all on what happens at larger distances. It's just that the details don't matter much. Large things are made of smaller things, and the laws for the larger things follow from the laws of the smaller things. The surprise is that the laws for the large things are so simple. And I guess she's talking about gravitation, because the laws for molecules in living systems are far from simple. Nobody's even tried to write them down. But let's go on. Much of the information from the smaller things, it turns out, isn't relevant to understanding the larger things. We say that the short distance physics decouples from the physics at larger distances, or that scales separate. This separation of scales is the reason why you can go through life without knowing a thing about quarks or the Higgs boson, or, to the dismay of physics professors all over the world, without having any clue what quantum field theory is. This separation of scales has far-reaching consequences. It means that we can devise approximate laws of nature that, to good accuracy, describe a system at some given resolution, and then revise these laws as we increase the resolution. The approximate laws, which are good only at a certain resolution, are called effective laws. As one decreases the resolution, that paragraph could have done with some more, but as one decreases the resolution, it is then often practical to adapt the objects that the theory deals with, and also the properties that we assign to them. In the theory at a lower resolution, that is, at a larger scale, it might make more sense to collect many small constituents into one larger object, give a name to that large object, and assign it properties. This way we can speak of atoms and their shell structure, of molecules and their vibrational modes, and of metals and their conductivity, even though in the underlying theory there aren't any such things as atoms, metals, or their conductivity. only elementary particles. Each level of resolution therefore has its own language, which is the formulation most useful on that level. We call these resolution-dependent objects and their properties emergent. The process that relates the theory for short distances to the one for larger distances, also referred to as coarse graining. Emergent is the opposite of fundamental, which means that an object cannot be further decomposed and its properties cannot be derived from a more accurate theory. That's what fundamental means. Being fundamental is a matter of current knowledge. What is fundamental today might no longer be fundamental tomorrow. What is emergent, however, will remain emergent. Matter is made of molecules, which are made of atoms, which are made of standard model particles. The standard model particles plus space and time are, for all we currently know, fundamental. They are not made of anything else. In the foundations of physics, we are trying to find out if there is something even more fundamental. As a physicist, I'm often accused of reductionism, as if that were an optional position to hold. But this isn't philosophy, it's a property of nature, revealed by experiments. We have extracted these layers of resolution and their laws from countless observations and found that they describe our world dramatically well. Effective field theory tells us we can, in principle, derive the theory for large scales from the theory for small scales, but not the other way around. The history of science has slowly revealed this hierarchical structure. The history of science has slowly revealed this hierarchical structure is why today many physicists think that there must be one fundamental theory from which everything else derives, a theory of everything. It's an understandable hope. And then she makes a silly joke about chewing gum. But when you decide to budget and build something like the LHC, you do the whole thing in terms of emergent properties of matter. Those magnets and those beams are constructed, and those detectors are constructed using macroscopic properties of matter. And we infer the existence of these fundamental particles like quarks and gluons from the results that we get from these countless observations. It would actually be pretty easy to put an upper bound on the number of observations that have been made, but this is the thing the assumption that the physicists seem to be very happy to make a lot of the time in a lot of different parts of physics, not just in high energy physics, in other physics as well, is take the first thing that explains what you're seeing. It's usually the simplest thing you can come up with that fits the observations, and then call that the reality. And I think that step has been made again and again and again and again, and the result is a model which I don't know what the real basis for saying that is the fundamental nature of reality is. It's basically that we can't imagine anything else producing that, and that's such astounding failure of imagination. I wonder why these people even have jobs. I don't get it. And a good example is black body radiation. And this is in all the standard undergraduate. When you teach undergraduates quantum mechanics, you base it on 2 or 3 experiments, and one of them is the black body radiation curve. The only thing that could produce that curve is quantized energy in the oscillators that are in the inside of this black body and causing it to radiate. Because nobody has been able to come up with another model. The answer is it must be quantized, because we're unable to imagine any other reason. And that's not a fundamental, that's not a fundamental law of nature. It may be a fundamental law of human nature, but it's a very sad one. So I'm just, this is why I'm not interested in physics. This is why I don't want to be a physicist. Despite thinking I wanted to be a physicist and going to the trouble to do a degree in pure and applied maths, when I finished that degree and I looked at what the next step was, it wasn't there. There was no next step. It's just a tissue of politics and big talk and shoving your ideas down people's throats and refusing to listen to anything else. It's horrible. It's horrible. I don't want anything to do with it. Sorry, Sabine. I've probably read as much as I can manage of your book. It's I'm on page 45 or something. I don't want that stuff in my head. Sorry.